Thank you for coming. It's really exciting to see all of you here. I am Jillian Bellavary, the director of the Masters in Astrophysics program at the CUNY Graduate Center. And this is the celebration of our graduates of our very first cohort ever, which is so exciting. I'm going to dance up and down the whole time, probably. These students have been in a program for 2 years. They have taken a bunch of classes. Some have been awesome, some have been a struggle. They all did great. And they've also done a research project with a research mentor that they started in the beginning of their time, but then ramped up in intensity, and they ended up writing, or are in the middle of writing for some of them, a master's thesis. So some are graduating next week and walking in the ceremony. Others are going to graduate in August or September, and they don't get to walk in the ceremony, but they are still being celebrated here awesomely. We have, there are 5 people in the cohort, but one of them had a last minute family emergency and couldn't make it. So we are going to have 4 presentations today. They are going to be about 12-ish minutes, and then there will be time for questions. If you in the room do have a question, please use the microphone system that was described in the video, because there are people on the Zoom who will want to hear. And people on the Zoom, if you have a question, the chat is being monitored, so feel free to ask in the chat and your question will be communicated. All right, with that, I would like to invite our first speaker, which is Master Andrew Ayala.
Testing, all good? Okay. Let's see if I can stay under time here. Okay, hello, good afternoon, everyone. My name is Andrew Ayala. I'm a graduate, or graduating from the CUNY Masters in Astrophysics program. Today I will be presenting a work called Pulsey, a Python program built with the aid of my research advisor, Keaton Bell, who's a faculty at Queens College. It is a tool for modeling stellar pulsation and stereoseismology. So let's get into it. First, I'm going to start with a primer on stellar evolution and pulsation. I'll be making some basic assumptions about the audience's knowledge regarding light curves, photometric analysis, and periodograms, things of the like. So first, we start with a nebula, a cold, massive cloud of dust and gas, which collapses under its own self-gravity into various different forms of stars, be they main sequencer, high mass stars, red giants, white dwarfs. And all these stars have the potential to exhibit some form of stellar pulsation in one way or another. This moves us into the regime of stereoseismology, where we can probe these stellar interiors. The picture most people have in their heads when they imagine stellar pulsation is a star, something like the sun, that's kind of increasing in temperature or brightness, getting hotter, and then due to energy conservation laws, cooling back down, getting darker again, and then that cycle repeating over and over. Here you're seeing a GIF of a radial pulsation with a light curve that indicates how that luminosity or photometric value rises and falls over time. The 2 mechanisms of this are what are known as pressure modes and gravity modes. These are basically in pressure modes, you can think of them as like acoustic waves, or kind of like sound waves traveling throughout our stellar interior, where certain layers or radii are sensitive to certain frequencies. Whereas gravity modes, you can think of these more buoyant forces, where there are layers or stratifications of our star that are more condensed and are feel stronger forces of gravity compared to other layers. And here we can see a figure where these regimes kind of fall, these P modes and G modes, pressure modes and gravity modes respectively, where as they relate to solar radii and the kind of frequencies we can expect in these regimes. And they are identified by the Brunt-Weisel frequency, which relates the gravity modes to various parameters such as density, surface gravity, pressure, and the Lamb frequency, which speaks to the pressure modes of also using rho, density, sound speed. And we can see that there's an overlap in this figure around that white section between the blue and orange, where we can actually witness both what are called mixed modes, pressure and gravity modes occurring in our solar system. So there are two main drivers or mechanisms that push these stellar pulsation modes. The first is what's known as the Kappa mechanism, which is also known as the Eddington value. This refers to an opacity variability that we can see within the star. Basically, there are these stratified layers you can think of as the hot surface of our star, and below it might be a darker region. Because it is darker and more opaque, it's more susceptible to radiative transfer and receiving heat. Thus, it receives more heat, this layer expands, it becomes more opaque, and this cycle continues where it can receive more heat until a critical point is reached at which the opacity eventually needs to give way to efficient radiative transfer and cooling a neighboring layer. And that cycle repeats between these stratified layers. The physical mechanism behind this is believed to be these changing ionization states within these stars. So the chemical makeup affects the radiative transfer properties of the different stratified layers of our star. Some examples of stellar systems that exhibit these are Cepheid variables that we might be familiar with. I'm hearing an echo. Someone on Zoom is not muted. And Cepheids are Lyra and Delta Scuti. What's responsible are these helium ionizations in gamma Doradus and some of these B-type pulsators. We can see heavier metals such as even iron, and in DOV or GW for white dwarfs. And the other mechanism is the more familiar convective transport and turbulence, where the envelopes of plasma basically give way to strong turbulent flows and exchange energy that way. And these perturbations propagate throughout our star and manifest as pulsations. And some examples are main sequence stars, solar-like oscillators, and giants, and the DAV and DBV white dwarf pulsators. And here are a couple examples of light curves. With the Cepheid variables, we can see very high amplitude variability on relatively longer timescales on the order of days to weeks. Whereas with a DBV white dwarf, we see these very short very high frequencies, short periods of on the order of minutes to dozens of minutes, and lower amplitude. So here's a brief HR diagram exhibiting stellar pulsation regimes, the various stellar pulsators I mentioned, DAVs, DBVs. Here are the regimes where we expect that the Kappa mechanism to be a stronger driver of stellar pulsation, whereas in the DAV, DBV white dwarf regime, the main sequence star solar-like oscillators, convection and turbulence is more the driver. So in the heavier, more massive stars, the hotter stars, we expect this Kappa mechanism, this Eddington mechanism, to be the main driver. And for these lower mass or more evolved white dwarfs, we see convection turbulence being the main driver. So now this moves me on to my Python package that I built, Pulsi, which will model these kinds of pulsation. So the fundamental structure of Pulsi uses a common concept that we see arise all over science, whether it be chemistry or quantum mechanics, and now even stellar pulsation, which is this concept of spherical harmonics. So simply put, not including a radial radial mode, just considering these L and M modes, which are more translational modes. The L refers to the amount of nodal lines, these white kind of crossings where you can think of the white as the median or the average temperature or pressure or surface gravity, whatever parameter you're matching, luminosity. And the blue and red regimes are the extremes, the peaks and the troughs of the wave, where the blue part might be the hotter or brighter part of our star, and the red part might be the colder, darker spot. And you can imagine these two regimes sloshing back and forth while the nodal line remains at this median or average. So that's the foundational structure of pulsy. So we can see what happens when I apply frequency, amplitudes, and phases to these fundamental spherical harmonic modes. As you can see on the left side, they create sinusoidal wave patterns because we're basically seeing a very simple sloshing back and forth of a disk, of an integrated flux on a disk. But when you add up these modes, you get something that looks more "quote unquote" natural, a more random looking pulsation that might look more like something we see observationally. So considering this, the fundamental goal with pulsy is to kind of match or figure out what pulsation modes we're witnessing when we look at a photometric light curve to determine the interior structure of our stellar source. Below, you can see a light curve that basically shows what the disk looks like over time and how that integrated flux manifests as a photometric light curve. Another powerful tool that pulsy can do, which it's built on top of Starry, a Python package made by a fellow who's no longer here with us at the CCA, Rodrigo Luger, built the capability to make binary systems. So what we can do now is make a primary pulsating star with a certain photometric variability and add a secondary to eclipse it. And this proves to be a very powerful tool in terms of probing what modes we're actually seeing, in the sense that we can break degeneracies. So as you can see on the left side, say we had a star or source with a single mode, but those modes were different, as we can see with the top L1 M0 and L1 M1. You can imagine if they were oscillating at the same frequency and we were just looking at a pixel on a CCD rather than a model from Python, it would be impossible to tell what actual mode we're witnessing with this photometric variability. However, during the time of transit of an eclipsing binary, we can have our secondary basically scan across the surface and cover certain parts of our star, whether they be more hot regions or colder regions. And what that does is break this degeneracy in a sense during that time of eclipse. So on the right-hand side, you can see a bunch of modeled light curves where I've subtracted out the dip that occurs due to the eclipse. And what you're seeing are different modulations that occur during the time of ingress and egress of eclipse. For example, the bottom 2-2 mode gets slightly amplified before shrinking back down at the point of the midpoint of eclipse, whereas the 2-0 mode dampens out very quickly. And if you had a system or were able to model a system, you could actually tell the difference between these two things during these two modes during eclipse, rather than them just being sine waves. So extending pulsy and future work. So far, I've shown you models of eclipsing binaries and single stars, but ideally we can use these to probe more interesting objects, more specifically white dwarfs, which prove to be very coherent and pulsating stellar sources. For brief information, white dwarfs, imagine something that's the mass of the sun compressed to the volume of mass and temperature of the sun compressed to the volume of something about the size of the Earth. And the core differences between these two are, whereas you have a radiative zone that gives off energy to a convective layer in a main sequence star, in a white dwarf, it's basically all core with a very thin convective envelope. And that core is held up by electron degeneracy pressure, combating the force of internal gravitational pressure. So we can think of this as basically one big atom that is held up on its own and has this kind of convective envelope around it. So these white dwarfs are ideal pulsators in that they exhibit very rich pulsation and very strong power in their pulsation modes, specifically when they're in the hotter regimes. As we can see from the top going down from the red to the orange, we have very coherent high frequency pulsation modes that as the white dwarf cools down to those purple and orange tracks, we see those amplitudes start to not only get dampened out, but those frequencies actually drop significantly. But nonetheless, white dwarfs prove to be a very rich environment to probe stellar pulsations. They also exhibit interesting phenomena such as pulsational outbursts, which occur, as you can see, at the bottom left of the figure. That's the kind of normal pulsation mode with this green kind of outburst occurring at points in time, which also on the right part of the figure, you can see the pulsation still being exhibited. And PULSI has the potential to model phenomenon like these. By gridding our surface, we can get a better understanding of applying things like SED tools or tracking things like gravitational, local gravity, local pressure values, and see if they fall within regimes we expect or if they exceed certain critical limits. And that can be an indicator of something like if we expect a pulsational outburst on a certain part of the star by examining specific parts of it. I'm running out of time, so okay. Very quickly, the last interesting phenomenon we can inspect with PULSI are these novel phenomena of tidally tilted pulsators. We're familiar with stars that orbit each other, but in binaries, specifically white dwarfs with a companion, fall into the system as they radiate their gravitational waves, and angular momentum starts to send these two objects closer to each other. The Roche lobe of our companion objects of the white dwarf kind of starts to get sucked into the gravitational pull of this white dwarf, and eventually leads to a type 1a or a dwarf nova. But the interesting part that PULSI has the potential to probe is this kind of a beginning process when the secondary starts to get elongated or a more oblong structure, in that we start to see these photometric variations due to the geometric effect of the tidally tilted secondary. And that's something that PULSI has the potential to model. Last but not least, just want to mention some current hurdles that exist. You have to, PULSI is a little outdated because it's built on top of Starry, which hasn't been kept up due to its creator leaving the CCA. So there are some issues and hurdles you need to get over when installing it, such as creating Python environments and all sorts of pip installs. And my documentation, as you can see on the right, in PyPy is lacking. So there's still some more work to be done in terms of keeping this up to date and making it very user-friendly. But I believe it can prove to be a very powerful tool for stereoseismology. I was hoping to walk through a very brief Python tutorial, but we don't have time for that, it seems. So questions, if you got them, and I'm sure you do. Thank you. Thank you.
Andrew did not actually leave any time for questions, but Amani, are you next? Who's next? Yeah, why don't you switch the computers and Julianne can ask a question.
I mean, that was just absolutely lovely. And I just want to let you know that Leonel Garcia, who's an FRF in the CCA has like taken over and built kind of almost a next generation Starry. So like there's an even better replacement for Starry that is being created, and y'all should talk.
All right, someone to I'll definitely come see you, Julianne, after.
Oh, that's Lionel Garcia.
Okay.
I will just, you'll come see me and I'll say goes.
Okay.
But I think he's out of town right now.
Thank you.
Awesome.
I have a question. How many you used to get this information?
Which information specifically?
All the stars.
So there, what I'll be using for observational detections are space satellite missions like TESS and Kepler, which have tracked various stellar pulsators, but specifically what I'm interested in are white dwarf pulsators, which I mentioned, which have been tracked by these two space satellite missions and have given troves of data and are still giving out data. TESS is still going, and yeah.
All right, if you have more questions for Andrew, you should ask him in the reception afterwards. Let's thank him again. And our next speaker is Master Imani Dindi.
Okay. How's everybody doing? Thank you for answering. My name is Imani Dindi. Funny story, I'm a CUNY graduate with these guys. It's been fun. Thank you, Jillian. My advisor is Ari Maller, and it went away. That's fine. Okay. Basically, what I did was there is this large simulation called Illustris and TNG. I took data from that and applied machine learning to it, and I wanted to see if I could make some relations between black hole mass and the properties of the galaxy that are formed in those simulations. So I have 4 key takeaways. The last one is kind of iffy. If you would like to ask questions, you can. I do have a slight answer for it, but we shall see how that works out. But I do find that there's a resolution issue with TNG 100 and 300, which is odd. I also find that you can make a very good estimate for black hole mass with just using only 4 features. We started out with 12, so that would cut down on time ran in your code, which is necessary. And then I also see that the symbolic regression fails to make a simple equation for TNG 50. It was giving back things with like e to the 5 billion something. And I was like, okay, that's probably not useful in any way, shape, or form. So I got rid of that. And then also that these are basically simulations attempting to model the exact same thing. So you would assume that these equations that I found would be interchangeable, but between 100 and 300, they are not. So there is some issue there, but again, like I told you guys, there is some caveat there. So I will explain that later. I'll do a little bit of background into the TNG. Essentially, what they are, just cosmological simulations. Just 3 different sizes. Basically, it's the resolution of them. You have 300, 150. You see them at the bottom right over there. And so basically the only thing that is necessary for you to know is that there should be a very big similarity between 300 and 100, but we still don't see that. It just doesn't make any sense because they're supposed to be very similar. But anyways, okay. So on to what I actually did. So after making necessary cuts, basically just there's certain ranges between stellar mass that should be similar, because if not, things would get kind of wonky. But basically, I did a ton of true versus predicted plots, and in machine learning, I use random forest. Does anyone know what that is? Good. Okay. But essentially, for anyone who doesn't know, it's a black box. Okay. You throw in your information, and it outputs what you want. And so what I want is on the left, and that's to predict it, and on the bottom is true. So it's already what we know. So we're assuming that we know what's already going on just to see what we can get. If you look for the TNG 50, which is at the bottom, it looks relatively, what would that be? Not flat, but like correlated. It's a straight line.
This is going to present her presentation on her graduation. Yeah. I told her I'm watching. I'm gonna record it. How about water? Come on,
God,
baby.
is that you? Whoa, okay. Anyways, so so it's very correlated for TNG 50. But if you look at 100 and 300, they're these like very uncorrelated regions. And for the longest time, we couldn't really figure out why. Most of the time, it's usually user error. So I thought I was messing up somewhere, and my advisor was going, "You're probably right about that. You probably messed up somewhere. This doesn't make any sense." That's not what happened, though. So I spent way too much time on that. What actually happened was, so all of these simulations are made with, they're called resolution elements. Essentially, what they are is just basically like gas particles in the universe is what they are. And so they are all different sizes for each simulation. If you divide out that resolution element for all of them, or all of the black hole masses, it now becomes like how many number of resolution particle per black hole in the simulation, well, in the central black hole you have. And when you do that, the uncorrelated regions match up. And so that was our first like hint that this was like a resolution issue for 100 and 300. So this is interesting because we could also see that is this affecting at different was that redshifts? We didn't get a chance to do that because the program's ending. but in my free time, I'm probably going to check that out because it's kind of interesting. But so we just did redshift 0, so like in the here and now. And so we get this. And so for us, it kind of makes everything very difficult to work with because our plots don't make any sense and it just doesn't help us anymore. So for now, we just decided to cut it out. When you cut it out, you get these really, really nice true versus predicted plots. These scores here basically are telling you your model is doing well or if it's doing bad. So R2, the closer to 1 you get is better, and MAPE is the lower it is, the better. And so for all of them, it's relatively decent. And then so knowing that, we decided, okay, so we've started with 12 features. Observationally, maybe we could make it easier for someone if they decided to use some idea like this. Could we cut down on how many features we have? I told you this in the beginning that we did. Okay. So we started with 12. We did a feature importance, which is very common. This was cumulative. So basically what we did was you start the code with, say, which one gives you the highest score, and then you continue to add on which one, more and more and more. And so for each of them, you basically get the highest or best score with just like 4 features. And so that made everything a lot easier to continue to make our equations to model these black hole masses, which is what I did next. So we used a symbolic regression tool in Python called PySAR. It's again still machine learning. It's a lot harder to explain than just regular machine learning because you just kind of have to let it do its thing. I ran it maybe 18 times for each one. Sometimes it worked, sometimes it didn't. That's technology. I don't know what to tell you. But they do have like a really in detail paper that kind of explains everything that they do, which sort of helps. But so yeah, so we get these equations for 100 and 300. I labeled them on top. And with these equations, for themselves, they work very, very well. Like for this one is trained on the 100, and you get like basically the same R2 score that you would get if you were to do just like an actual like or not symbolic regression, an actual machine learning model. So that was nice to see. With the 300 though, it seemed like it's still a relatively decent score, but it's not as good, and so we're not sure why that is. And so this is then where we thought to maybe use the equations from one box and then interchange them between each other box. But before I get into that, I would like to bring up there was something else. So there is a few papers, and I have them listed at the end, but there are evidence that a lot of these features are highly correlated in like observationally. And so like we would expect like velocity dispersion and I think it was a star formation rate to be very correlated with black hole mass, but we weren't seeing that in these equations, which didn't make it to us. It didn't make any sense. So then I used a heat map to decide which features were more correlated with one another. And so we do have these, and then we do see like velocity dispersion is very highly correlated with star metallicity, which was in our previous equation, and also Vmax and Vmax red. For these feature names, I do have a list of them and what they actually are. So if you want them, I can show them later, but right now it's just not too important. So I took these features that were highly correlated and again, use the equation that I found and then optimize the equation. And then this is just for the 100. But even doing so, like the equations don't get any better. Some of them kind of get worse. And so I don't know if this is just because we're not actually seeing what's truly happening just because I'm optimizing and not using like some sort of machine learning tool or what. And so that would be something interesting to look at in the future. But that was just something that was just a quick aside. This is if you just use the equations that I found directly into another box interchangeably. As I said, TNG50 was not too useful, so I didn't actually put that up here. But like you can see that with 100, you can kind of estimate TNG50, but you can't really estimate 300 too well. And with 300, it just kind of did poorly across the board. So we weren't too sure what was going on there either. But we I don't know. We're trying to figure that out. So yeah, that's basically it. So yeah, thank you for your time.
Does anyone have questions for Imani? Justin.
Yeah, on your symbolic regression plots, what causes almost in order, it looks like they're predicting an entire order of magnitude higher in black hole mass for true versus, see, you know what I'm saying?
Yeah, just like too much above and too much below.
Well, what I'm saying is, in the 300 plot, it starts at 10 to the 8th, and then in the 100 it starts at 10 to the 7th. So it's
okay, hold on.
Okay.
I can explain that. So the mass ranges between them are very different, like between the boxes themselves.
Oh, okay.
And so remember when I talked about the resolution issue and where they lined up?
Right.
They only lined up because I divided out the resolution issue. So they start at their own like respective mass issues. So that's where I just made the cut at, basically.
Oh, okay. No problem. I was just curious.
Juan, you had a question?
Yeah, Layman here. You might have mentioned this. What does TNG stand for?
Ooh, what that I couldn't tell you.
Oh,
I
okay.
actually don't know what TNG stands for.
No problem. Thank you.
There they go. It's
Okay.
like Star Trek or something. Right?
Any other questions for Imani? Yes, in the back. Please use the microphone button, everybody.
For the heat map, how did you capture the heat? Like, how do you? I don't know if you explained that. The chart where you show the heat.
Mhm.
How is it that you capture the heat? Like, how do you get the results for that?
Oh, okay. Yeah. So I just use, if you use pandas, they have like a very straightforward, you put in your features and it will output what like the actual like values basically. Basically it's just a whole bunch of like varying each feature one at a time and seeing what changes based off of that. And so that's how you get these numbers. So I'm not doing this by hand. I don't know. But it's just a panda package basically.
Austin.
Excellent job. I was just wondering if you've done investigations for your like a whole galaxy sample versus separating satellites and centrals and whatnot.
Oh, so yeah, I'm doing strictly central black holes, not satellites.
Okay.
Sorry. Do you have an idea about why you're seeing that discrepancy for lower mass black holes between the model mass versus what you are kind of saying is the true mass? Because you you decided
Oh,
to
the
do
resolution issue?
yeah,
Oh, yeah. So my assumption is, so of course, like these simulations aren't like fully modeling what the universe is doing. So once the galaxy hits some like threshold, it'll seed in a black hole. My assumption is that these are being seeded in and they haven't had time to actually like, what was it, mesh with the galaxy that they're in yet. So it's just, there's no correlation between what the mass actually is versus like what the property of the black hole is. So once it has time to actually be in the system for a little bit, I assume it would be a little bit better, but I'm assuming that's what's like the problem here.
All right, we have time for one more question, but can you switch the laptops with the next person and plug yourself? You had a question?
Yeah.
Please use the microphone.
Space travel or communication. Is there any application for this research?
For
space travel or communication with other planets or something. What's the application of this research, basically? Any practical application at this moment?
Oh, geez. I don't know. I don't know.
Yes.
Do you want to?
Imani, you can think about it during the next two talks and then ask him
got it.
after.
Yeah.
All right, let's thank Imani again. And our next speaker is Master Rosario Cecilio Flores Eli.
Stuck saying my whole last name. Oh, all right. Hi, everyone, and welcome to this presentation. Today, I'm excited to share with you and present the research that I worked on with my research advisor, Dr. Jacqueline Faraday, and the BDNYC research team that most of them are here. So hello, and on Zoom. I conducted this research at the American Museum of Natural History. Now, this presentation is going to be divided into 3 sections. In part 1, we will explore the world of stellar rotations. In part 2, I will branch out from stars a bit and I will discuss the celestial interactions with moons within our own solar system. And then I will wrap up the talk by discussing some future prospects for exoplanet and brown dwarf research. So let's get started. I have really cool animation, so I'm gonna take a second so you guys can see. So part 1, a brief story on stellar rotation. So in 2018, NASA launched the Transiting exoplanet survey satellite, also known as TESS, which is a space observatory designed to look for planets orbiting around nearby stars. Now, TESS surveys the entire night sky using 4 cameras, which together collect light from stars in successive swaths of 24 degrees wide by 96 degrees long. Now, these cameras work in 2 modes, capturing 2-minute cadence exposure of the brightest stars and 30-minute exposures on every other star. Now, the main objective of TESS, again, is to find these planets orbiting around stars through identifying through something called the transit method, which is, it just means when a planet passes through its host star, between the host star and us. And that's how we're able to capture very dip in brightness. Now, TESS can also provide data on stars, such as their rotational periods. This is a very fast animation of it. It can also tell us if it contains star spots, or if at time of observation, if there is any flare activity. And all of this can be done by looking at its light curve. Now, the light curve is just a graph like the one you see here that displays the brightness of an astronomical object over time. Last year, I had the opportunity to collaborate with some members of the BDNYC team, where I helped analyze around 100 light curves, about 100 light curves, like the one you see right there. And it was part of a broader study to help characterize the age of brown dwarf companions by observing the star they are co-moving with. And now, before I continue, because I know some people in this room don't know what a brown dwarf is, so I will quickly define it. So a brown dwarf is a substellar object with a mass between those of gas giants and this lightest of stars. Now, it cannot sustain hydrogen fusion in its core, and determining their age can be challenging, as there is change in luminosity and temperature, making them hard to distinguish between older brown dwarfs and young planets or exoplanets. Now, our star companions help by providing a reference age, assuming that brown dwarfs and that star companion form together. Now, by determining the age, we can determine the age of this brown dwarf. And this is called benchmarking. Now, let's come back to our light curve. As I mentioned earlier, I helped analyze around 100 light curves. And this is the light curve of object CW0256. Now, on the top panel that you see there, it just shows the brightness of the observed object over time. In this case, this object was observed around 60 days, or we have data on around 60 days. And on the y-axis, we just see the percentage change in brightness. Now, on the bottom left, left corner, we see just a test cutout image of the object we're observing. And if you can see, there are some stars, visible stars around it. And in the middle bottom part, we see a periodogram, which is just a plot that tells us, give us an accurate calculation of the period, rotational period of this object. On the x-axis, you see the number of period in days, and on the y-axis, you see its power. The higher the peak, the more accurate this period is. So in this case, this object is giving us a period of around 0.81 days. So this is a very fast rotating object. Now on the bottom right, it's just a phase light curve. Just picture these two, the light curve above, and it gets kind of pancaked and like a crab, like they call it. So out of those 100 light curves, 10 had strong period signals. And the table above, you can see 10 of the objects that I was able to analyze. Many of these objects have very fast rotational periods, less than a day, meaning that we are observing a very young group of stars. Now, when you have young stars, they tend to have a lot of magnetic activity, which we kind of see, going back to the plot, that little section over there, it's a flare. So it's just the object burping in some case. Okay, so based on the research that I did for this, these findings were published in this paper where I am co-authored, and it's led by Austin Rothermich, who is a doctoral candidate and also part of the BDNYC group. Okay, so now we're gonna move on to the second part. And I think I'm doing great on time. All right, so we're going to branch a bit away from stars and come closer to home. Now, one of the biggest curiosities that kind of guided me or led me to become interested in this field was the question of whether life as we know it exists outside, beyond Earth, right? Or worlds like Earth. Now, life as we know it requires 3 ingredients. It requires energy, it requires organic molecules, and it requires water, liquid water. Now, I discovered that there are worlds within our solar system that contain the essential ingredient, and that is liquid water. Now, in 2020, I learned that liquid water exists not on a planet, aside from Earth, but on a moon. This is Enceladus, one of Saturn's moons. Now, Enceladus is known to be an ocean world. What is an ocean world? An ocean world is just a celestial body that possesses liquid water above or beneath its surface. Now, we believe Enceladus has a subsurface ocean due to its activity, a plume activity of water vapors and ice particles spewing from its south polar region in an area known as the Taiga Strait. Now, this discovery it opened a whole Pandora box full of questions, and it did not stop there. I also learned that Enceladus is part of a network of other geologically active moons. And all of these moons orbit the gas giants, Jupiter and Saturn, and the ice giants, Neptune. Now, Jupiter hosts a moon, Io, that is the most volcanically active planetary body or celestial body in our solar system. We also have Europa, another of Jupiter's moons that it's also an ocean world and that we believe has a subsurface ocean. Ganymede is the largest moon in our solar system and has its own magnetic field. And then we go into Saturn. Saturn also hosts another geologically active moon called Titan. This one has a dense atmosphere and Earth-like surface features. And last, we have Triton, which is one of Neptune's moons and has activity of geysers spewing nitrogen gas. Now, out of these 296 objects of natural satellites, all of these orbit the gas giant. Okay. Bear with me. Now, with this in mind, and a little bug in my head, I began to question, can gas giants act as hosts for active worlds? And creating kind of like their own miniature planetary system where these objects interact. And now, can we draw these observations between planets and moon to start planet systems beyond our own? Now, sorry about that. So the short answer is yes. And today I'm only going to give you a very small piece of a large, bigger Jenga puzzle. Now, last summer, I delved deeper into this topic, inspired by 2 studies conducted by my mentor, Jackie, that focused on finding the mass ratios separations and binding energies of ultra cool brown dwarfs co-moving with stars. Now, I decided to do the same by investigating what the mass ratio separation and binding energies can tell us for planet moon systems in our solar system. And what can that tell us? Now, the mass ratio separation and binding energies help us understand the dynamic stability and formation mechanisms of these worlds. Now, my objective for this study was to see what patterns I could find around the active moons by looking at these parameters and whether they could give us a hint of something wider. Now, I took one of the, well, I'm about to explain. The plot behind me contains mass ratios and separations of star binaries, brown dwarfs and planets, for one of the papers I just referenced. On the x-axis, you have their separation, which is just the distance between two objects, celestial objects, and on the y-axis, you have the mass ratio, which is just taking the mass of the smaller, I would say, less massive object and divide that with the mass of the larger object or the primary object. Now, these objects roam from very large, widely separated, and more massive on the top right corner. And it kind of trickles down as the separations become more tightly knit and the masses become also smaller. So to summarize it, we have stars, we have brown dwarfs, we have exoplanets all on this plot. And I took those objects and I decided to take them with me and create my own plot. And this plot, I used the same parameters. On the x-axis, I took the separation in astronomical units and the mass ratio. And with the same objects that you saw previously, I plotted them right here. They just look a little different. And I added a new addition. I present to you the mass ratios and separation of all the moons in our solar system. Well, most of the ones I was able to collect data on, around 294 objects, natural satellites. Now, with the help of 2 high school students last summer, they helped me collect their mass values and their semi-major axes. I took the semi-major axes values and I just converted them into astronomical units so I could be able to fit them into this plot. Now, because of sake of time, I just noticed I'm running out of time. So what you see, I color-coded the moon systems. Earth is the lonely green dot above Triton. And then we have Phobos and Deimos right below the word Saturn. And everything else, Jupiter and Saturn are in orange and in blue. And all of Uranus, Neptune, and the dwarf planets, their satellites are in pink and in green and in red. Now, I really want to highlight the ones that are labeled in stars. Now, a big takeaway is that I noticed that the active moons that I've been speaking about all lie within a certain region in the mass ratio plot. And not only that, when I compared data with the objects that were originally there, there are some exoplanets that also share similar mass ratios, like Kepler 62f, which is a super Earth orbiting a K-type star. And I believe, and LHS 1140b, also a super Earth, but orbiting an M-dwarf star. All of these known exoplanets to be orbiting within habitable zones of their host star have same or similar mass ratios as these very active moons. Okay, so before I continue, I just have to say that it was a good insight and like I said, we only were able to get just a small little piece of a bigger Jenga puzzle. So in summary, to wrap things up with this section, is that I think it's important to not ignore the activity happening within these gas giant systems, because that can give us some overview or peek into these exoplanet systems. And I will briefly cover this part and then we'll wrap it up. So the future of exoplanets and brown dwarfs. So last year, my mentor Jackie told me about this interesting object that she got back data from. She observed 12 objects, or got back 12 spectral objects for 12 brown dwarfs from JWST Cycle 1 proposal. And sorry, bear with me. I want to make sure I'm saying the correct things. And the object that you see behind me, okay, so out of the 12 objects, one of the brown dwarfs came back giving an interesting spectral activity, I would say. Now, this object that you see here is very long name, but we all know it as W1935. Now, typically brown dwarfs show spectral features of water, ammonia, carbon monoxide, carbon dioxide in their atmospheres. But W1935 returns something different and unique, something that's never been seen before. Okay, and that is methane emission. And we don't know what's causing this. This object does not orbit a star, is a loner. It's also very cool, a brown dwarf. So we're trying to figure out what might be causing it. And to kind of end it there, we are investigating, or we're tapping back within our solar system, especially the aurora features happening here on Earth, in our solar system with Earth and the gas giants. And one cause for aurora activity on the gas giants is this little but mighty moon called Io, the volcanic moon, which, to wrap things up, causes aurora activity on its host. And as we can see there, there's Io's little footprint. And we're out of time, and thank you very much. And I guess I'll take questions now or during the reception. Thank you.
All right, while we switch computers, we can see if there might be time for a question. Shireen, did I see your hand? Go ahead. Please use the microphone.
Hi, Rosario. Congratulations on achieving your master's. Since it sounds like you had a really diverse experience with research, do you know what future research might look like for you, or what you're interested in, since you were able to delve into many different subfields?
I definitely want to explore active worlds that can, and specifically, I'm going to be moving on starting my doctoral studies at Cornell, where I will be working on geyser research. Thank you. Thank you. My research mentor studies geysers here on Earth, and we hope to, based on the findings, connect it back to Enceladus and Europa with their geysers. So I'm really excited. So anything that can hint us that's active, brown dwarf or exoplanet, moon. So yeah, I'm excited. So yeah, thank you for asking that question.
All right, we're running out of time. If you have more questions for Rosario, please find her afterwards. Let's thank her again. Our final presenter is Master Vanessa Brown.
Hello. Thank you everyone for coming. I want to say up front that I do not have cute animations like Rosario did, so please bear with me.
It's a hard act to follow.
It's a very hard act to follow. My name is Vanessa Brown, and my thesis is on magnetic draping in galaxy clusters. So I worked with Dr. Ulrich Steinwandel and Dr. Stephanie Thomason here at the CCA, and we were investigating whether magnetic fields affect galaxy evolution within clusters using cosmological simulations. Magnetic fields have been detected in and play important roles for astrophysical objects of all scales, from stars and planets to the ISM to galaxies and the media between them. The very hot gas within galaxy clusters, what we call the intercluster medium, has been shown to be magnetized through observations of diffuse, extended, and polarized radio emission. These magnetic fields are strengthened by processes associated with the formation history of the cluster. But how these magnetic fields may influence the structure or evolution of a cluster and its galaxies still remains unclear. Just briefly to describe what a galaxy cluster is. So these are the largest gravitationally bound objects in the universe. They are generally a few megaparsecs across, with typical masses of 10 to the 14 or 15 solar masses. They contain a large amount of dark matter, hundreds or thousands of galaxies, and hot plasma, which fills the space between these galaxies and is permeated by large-scale magnetic fields. Clusters aren't static, but they are evolving through external processes like major and minor mergers, as well as feedback from things like supernovae and supermassive black holes. And these interactions deposit energy into the intercluster medium via turbulence, shocks, and bulk motions. These processes drive the evolution of the intercluster medium as well as its magnetic fields. And these fields, which typically have strength of a few microgauss, are probably not significant dynamically, but we believe they do play roles in the microphysics and the energetics of the ICM, as well as the morphology and evolution of cluster galaxies. They provide an additional pressure term in the intercluster medium. They can affect transport processes such as heat conduction, and they also reveal the cosmic ray electron population through synchrotron emission. We do know that environments impact galactic morphology and evolution, particularly high density regions like galaxy clusters. Early type galaxies and quiescent systems dominate in clusters, while late type galaxies and spirals are more likely to be found in the field. We know that galaxies in high density environments also have suppressed atomic and molecular gas content, indicating that cluster galaxies or those in high density environments are more likely to be gas poor. There are several processes that can remove parts of a galaxy's interstellar medium, one of which we were looking at in particular in this project, which is called ram pressure stripping. So this is the removal of gas from satellite galaxies falling through the intercluster medium through a motion-induced pressure. And the key way to differentiate between RPS or ram pressure stripping and other cluster interactions is that, unlike gravitational interactions with other galaxies or the cluster potential, ram pressure stripping only affects the gas content of the galaxy. So we will regularly observe this acting on cluster galaxies, and we can see it by this kind of outside-in removal of gas with no effect on the stellar distribution of these objects. So we just see these long tails of gas, which can extend over 100 kiloparsecs in length occasionally. And the most extreme examples of these are called jellyfish galaxies, because that's exactly what they resemble. So an open question is whether magnetic fields in the intercluster medium are able to have any effect on this gas mass loss of satellite galaxies. We do see that objects moving super alphanically through a plasma like the intercluster medium can sweep up magnetic layers ahead of themselves, and that layer will then fold or drape over the object. This draping can potentially suppress transfer phenomenon, as well as hydrodynamic instabilities. So our question is, this buildup of strong magnetic layer around a galaxy, is it able to counteract forces that change the morphology of these galaxies? So is it able to kind of fight against ram pressure stripping? Here I have exactly one animation. Okay. So what we do to investigate this question is we run identical cosmological hydrodynamic and magnetohydrodynamic simulations using the code gadget. So we have one simulation that is run without magnetic fields, one simulation that is run with magnetic fields. And we're trying to investigate whether this magnetic draping impacts ram pressure stripping. So after we simulate this galaxy cluster, both with and without magnetic fields, we use this code Rockstar on the output to essentially identify halos within our cluster. We get IDs for them, as well as very generic properties of these halos. And then we use another package called YTree in order to get their merger histories and basically track the behavior, the mass evolution of these halos over time. And then finally, what I'm about to show over several slides are many projections and radio profiles of global properties of the cluster, as well as distributions for dark matter and gas masses of the galaxies that we considered in this project. So first we start with a projection of the gas density in the cluster. And what we can see is that on very, very, very large scales, the hydrodynamic simulation and the magnetohydrodynamic simulation pretty much look the same. And this is good because it means that our simulation didn't blow up. We do not expect magnetic fields to dramatically impact dynamics in these systems. What we see as we begin to zoom in, though, onto smaller scales is that there are slight differences that become apparent. And once we move down to the actual satellite scale, we are going to see how things are differing in between these runs. So what we're looking at is a zoom in on the cluster that I just showed. The circle is the virial radius of the cluster in white. And if it's not kind of clear where these differences are here, we can zoom in a little bit more. And now we can start to see some morphological differences between runs. So there are some galaxies in the HD that are morphologically unique compared to their counterparts in the MHD. So, excuse me. Although we see that the distribution of these satellites is quite similar in both of the runs, we do notice that the more diffuse gas around the satellites is behaving quite differently. And what I have here are just some examples that I pulled out and highlighted just to kind of show this phenomenon. So if we focus on these identical individual galaxies in both runs, we can see distinctions in the extent and the shape of these satellites in some cases. So this could be the presence or absence of tail-like features or bow shock-like features. And we can kind of see that many halos in the MHD run appear to have gas trailing them, which we don't, they may be absent or more truncated in the HD run. Actually quantifying the morphological differences is beyond the scale of this project, but we did want to just point out that they do exist. Okay, so here we see the radio profile for the gas density that we just saw projections of in both runs. The HD is in yellow, the MHD is in blue. And what we notice is that they exhibit nearly identical behavior. And the peaks in each profile do occur at the same radio locations. But the thing to kind of notice is that at any given peak in the MHD run, we see that these values are consistently a little bit higher. So what we're kind of seeing is that all substructure, despite occurring in the same cluster locations, is a little bit more collapsed than in the HD run due to what we found to be a slightly higher mass distribution in the MHD run. So I have a ton of these global properties to kind of get through. So enjoy the beautiful colors as we run through these. So what we're looking at were similar projections of temperature. First, we saw temperature around kind of the scale of the virial radius. And then again, if we zoom in, we see that temperatures in this cluster are around 10 to the 7 or 8 Kelvin, which are in line with X-ray observations. Just as with the density projections, there's overall a high level of similarity in both runs, other than maybe slightly lower temperatures in some of the trailing gas in the MHD run. But you'll have to squint a little bit. Here again, we see the radio profile for temperature, HD in yellow, MHD in blue. The temperature in both runs drops steeply toward the center, so this is indicating that this is a cool core cluster. I'll pick up the pace just a little bit to be mindful of time. Here we see entropy in the cluster, again, on the scale of the virial radius. And then we zoom in a little bit. We can see that there are a few deviations on the level of individual satellites. We can notice some slightly lower entropy values in the satellites on the MHD run. Again, if we squint. This is a radio profile for the entropy. We have characteristically low central entropy in our cool core cluster. The peaks in the entropy, which are pretty much identical in both runs, these are denoting the shocked region at the virial radius. We also have projections of thermal pressure, which show similar trends. And then the main difference here is if we kind of look maybe at the largest subhalo in the bottom right, we can sort of see where thermal pressure values seem to be slightly higher in the MHD. And this is also supported in our radial profiles here, where we kind of see the same thing we saw with density, where the peaks are slightly higher consistently. And then here's my favorite plot. This is the turbulent kinetic pressure within the cluster. Here we can see the greatest visual difference between runs. On the scale of the virial radius, we see kind of more distinct edges or fronts of turbulent kinetic pressure in the MHD. And we can see more defined and complex substructure as well. And then I'll just zoom in. We can see that the differences are a lot more stark in this case. And then if we look at the turbulent kinetic pressure radio profiles, we can see that overall turbulent kinetic pressure in the MHD run is around a factor of 2 lower everywhere. Pardon me as I skip through some plots just to keep us on track. The main takeaway for the global properties that we observed is that magnetic fields do not seem to have a major impact on most of the global properties that we looked at. Generally, the radio behaviors of each property exhibit similarities with or without magnetic fields. However, we noticed some pretty big differences in gas morphologies in and around subhalos. This could relate to the shape and extent of the diffuse gas around them, or the presence of things like tails or what appear to be bow shocks. So clearly magnetic fields are doing something, even if it's not hugely obvious on the largest scales. So to kind of take a look at the actual subhalo population that we studied, when we begin, we start out with about 100,000 objects in both the HD and the MHD runs. And we can see that the dark matter mass distribution is incredibly similar for both, with maybe skewing slightly lower for galaxies within the virial radius in the MHD run, but overall they're very similar. If we take a look at the gas mass distribution in both, we see essentially the same thing. These big columns on the left on both plots, these are galaxies that did not have any gas associated with them. So that's what those features represent. I made a ton of cuts to these 100,000 or so objects in both runs to get a sample that we were interested in studying. So we made a simultaneous mass and redshift cut, as well as some location cuts to essentially find galaxies of mass significant to what we were trying to look at, as well as are in the final redshift and are within the virial radius of the cluster, because we want to look at infalling galaxies and what their gas mass histories are. And ultimately, what we do is we group these subhalos according to whether they experience an increase, decrease, or complete depletion of gas mass by the final output. And this is displayed in this 4-panel plot here. I will simplify things enormously by just summarizing. We found that in the HD run, about 73% of subhalos lose all their gas after crossing the virial radius, but that number is lower in the MHD run. So just something kind of interesting to notice about the gas evolution in both runs. We wanted to take a look at kind of the timing of these gas loss events. So we have a plot where we look at the total mass of these subhalos, as well as how many snapshots it takes them to lose this gas mass. And we see that the majority of them take between 1 and 3 snapshots to lose all mass, which is, just for some context, that's under a gigayear. And this is expected given the low density of the gas in the subhalos. However, in the MHD, so HD is yellow, MHD is blue, we do find in general that the quenching, or there's a distribution towards larger quenching times. Excuse me. If we want to put some quick numbers to this, the fraction of subhalos that take 4 or more snapshots to lose their gas is 19% in the HD run, and it's 25% in the MHD run. So I basically have no time, but what I wanted to kind of quickly mention as I wind down here is that we also take a look at the position of galaxies when they have complete mass loss. Overall, we find that in the MHD run, galaxies are making it further into the cluster before they experience total gas mass loss. And I have something like 300 halo history plots on my drive. They're not all here, which basically kind of shows the different sorts of histories that we saw with these subhalos. So some of them will retain their gas throughout the whole time that we observe them. Some of them will lose it right at crossing time. Some of them will lose it well before they hit the virial radius, et cetera, et cetera. So I'll leave us on my main summary slide. When we're taking a look at the distributions and at the snapshots to total loss and the location of total gas mass loss, basically what we find is that there does seem to be some mitigation of gas removal in the MHD run. So as it says here, the fraction of galaxies that retain some gas mass as they move through the cluster is higher in the MHD run. And these objects also take more time to lose that gas. So if we try to account for things like position in the cluster, and other kind of individual subhalo properties that could affect this. But overall, what I didn't get to talk about in my plots is that when we sort of bin these objects by mass, all of this information still falls out. So we feel pretty confident saying that magnetic fields absolutely have some sort of effect on morphology and overall gas behavior of these objects. Thank you so much.
Questions for Vanessa? Austin, is that a hand? Okay.
Just wondering if you had a chance to look at the loss rate for like different profiles, like if you were looking at like the CGM loss rate versus like an ISM loss rate, and if there was any differences.
So if I understand your question, we're not like simulating like true galaxies. So we're not like looking, we're not looking at actual like subhalo structure necessarily. So I don't think we're able to like compare it on as fine like that scale, if that makes sense.
More questions? Josh.
Wonderful talk. I really enjoyed it. I'm curious about, I know you said you didn't want to delve into the quantitative discrepancies or differences between MHD and HD, but do you have a sense for which of these morphologies is closer to what we see in clusters? MHD or run actually closer to the morphologies of galaxies that we actually see in clusters?
That's a great question. I did not spend time comparing to observations, but that is a really tantalizing next step.
Andrew.
Great talk. So just to get a general sense of what's going on here, is the idea that they're a global structure of these clusters are kind of basically unaffected by magnetic fields, but in these smaller individual galaxies, their magnetic field strengths kind of act as sort of shields in the same way that the Earth gets shielded from solar winds by our magnetic field, and it's kind of containing the individual subhalo structures at the smaller scales while not affecting the global look or parameters of the larger galaxy cluster.
Yes, but my understanding is that it's not an internally generated magnetic field necessarily. You're sweeping up magnetic field lines as you're moving through the magnetized intercluster medium.
Thank you. That answered my question.
All right, let's thank Vanessa again.